This is section 10.3, starting on page 719, odds number 19. In circle H, the diameter is 18, LM equals 12, and the measure of arc LM is 84. Find each measure, round to the nearest hundredth if necessary. So mark in your given information first. The diameter is 18. Which means that our radius, so if I draw from H to L, that will be the radius, would be half of that, or 9. And LM is 84. So from here to here we have 84 degrees. I'm not sure if we need that for number 19. No, HP. So I'll erase that part. Alright, so we want to find HP. Alright, the best way to do this would be to first write in the rest of the given information, which LM we have is 12, and since the diameter is perpendicular to chord LM, the diameter will split it in half, which means that LP is half of 12, or 6. So I'm going to take this right triangle and move it over to here, blow it up a little bit. So I'm going to label that H, K, and L. So opposite from the right angle is my hypotenuse, which is 9. We can see that L, whoops, that shouldn't be K, it should be P. We see that LP is 6. And we want to find HP, so we'll call that A, use Pythagorean theorem. A squared plus 6 squared is equal to 9 squared. So A squared plus 36 is equal to 81. Subtract 36 from both sides. A squared is equal to 45. Take the square root of both sides. A is approximately 6.71, and A was representing the length of HP, which is what we wanted to find. So HP is approximately 6.71. Number 21. The curved road at the right is part of circle C. Let's see if I can make this circle right. Close enough. So circle C, which has a radius of 88 feet. So from C to B is 88 feet. And we want to find AB. So this chord is what? Round to the nearest tenth. Alright, so to find AB, we just have to find EB. Find EB and multiply that by 2, because the radius is perpendicular to the chord, so it's splitting the chord in half. So EB will be half of our answer, multiplied by 2, and we get the full answer. So AB is equal to 2 times EB. So let's find EB. So we have a right triangle. We'll split that off, draw that a little bit bigger. Where E is here, B is here, C is there. We know that our radius is 88. Let's see, what else? We also know that this small piece, DE, it says is 15. Well, our radius is also DC. So if I want a length for EC, I need to subtract 15 from that entire radius there. So EC is equal to DC, the radius, minus DE, which we are given 15 for. So 88 minus 15, and we get 73. So EC is 73, and let's find EB. So we'll call that A. Using Pythagorean theorem, we have A squared plus 73 squared is equal to 88 squared. 73 squared is 5,329. 88 squared is 7,744. We should still have A squared over here. So in our next step, we would subtract 5,329 from both sides, and A squared is equal to 2,415, and A would just be the square root of that. So approximately 49.14. So that is approximately what EB is. But remember, we wanted to find AB, so we need to multiply that by 2. So AB, which is 2 times 49.14, is approximately 98.3 feet. Number 23, in circle S, LM is 16, PN is 4x. What is x? So LM is 16. PN is 4x. Well, we have two chords that are equidistant, the same distance away from the center. So they're both 7 units away. We know that it's the distance from the point to the line because it is the perpendicular segment from S to this line segment and the perpendicular to this chord. So the distance is the same, therefore we can set them equal. If 4x equals 16, x is equal to 4. Okay, number 25. Let's do a little proof here. I know that it says paragraph proof, but I'm going to change this to 2-column proof. Of theorem 10.2, part 2, which basically states if you have a circle and you have 2 congruent chords, then the intercepted arcs will also be congruent. So based off of the fact that these 2 chords are congruent, QR and ST, can we somehow prove that these 2 arcs are congruent, QR and ST? So as we always do with the 2-column proof, on one side we have statements, and the other side reasons. Number 1, let's go ahead and state just the fact that this is a circle, that we are given a circle. So, given a circle, so what are all of these lengths? These are all the radii. Will they be congruent? Yes. So we can state that all of our radii are congruent. QP, PR, SP, and PT Okay. Next, what can we say? Let's state our other given information. That QR is congruent to ST. Alright, so what do we have here in our diagram so far? We have two triangles, QPR and SPT, that are congruent because all three sides of this triangle are congruent to all three sides of this triangle. So by side, 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 these two triangles are congruent. Side, side, side. Next, what are we going to say? Well, if we have two congruent triangles, then their corresponding parts will be congruent. So I can say that this angle is congruent to this angle because those two angles correspond between these two triangles. So angle QPR and angle SPT are congruent. And that's by CPCTC. Corresponding parts of congruent triangles are congruent. And that's enough information. So now we can say what we wanted to prove. We wanted to prove that QR is congruent to ST. And let's talk about this before we write it down. So why is this arc the same measure as this arc? Well, because their central angles are the same. So if their central angles are the same, then the arcs are the same. Done and done. QED. Alright, and we'll pick up there on the next video.